Okay, so what I want to start out with is actually, I mean, deals with the answer to the question that Mohsen actually raised last time, and he asked, can you try to give an intuitive explanation of what the correlation coefficient represents? So this is a figure that I promised you to show you. This is from Kevin Murphy's textbook. This is actually on machine learning, but this is an introductory chapter on probability and random variables. So what this depicts are scatter plots. Okay, so how many of you know or have an idea or can guess what scatter plots are? And these are two-dimensional scatter plots, by the way. Mohsen, are you familiar with scatter plots?
सर इन theory वो एक quantity के ज़्यादा सारी measurements को display करते हैं on two-dimensional plot.
Right, good. Right, so this would be, these are actually observations of two pairs of random variables, right? So, and you observe them in 2 dimensions. So when you get a point from that observation, you observe that point in 2 dimensions, where x is the x coordinate, so that's one random variable, and y is the y coordinate, which is the other random variable. Okay, and 2-dimensional scatter plots would be if you're drawing from a particular joint PDF or joint distribution, and you draw that and you keep on drawing it, you keep on observing those observations from it over and over again, and every observation you start plotting them on 2 dimensions, right? And that would give you a scatter plot, right? So the first that you figure that you see here is a scatter plot, but this scatter plot is really nothing but a straight line. Okay, so and the density of the points in a particular position actually represents the probability, right? So the higher the density, the higher the probability of points being in that particular region, right? So if you just look at the figure on the top, on the top left, you'd see that there are more points around the center here, and fewer points as you go towards the extremes, right? So there are few points here and there are few points here. That means it's more likely for those 2-dimensional points to reside on this, in this region, than they are to be likely to have to exist in this region. Okay? And moreover, in these 2 dimensions, what we observe is that there's a straight line relationship, right? What does that mean? What that means is y is actually equal to a linear or an affine function of x, right? Y is an affine function of x, right? And that means given x, you would always know what y is, and given y, you would always know what x is. And more importantly, there's a straight line relationship between the 2 random variables. And for this, the correlation coefficient, if you compute, that turns out to be equal to exactly 1.0, right? So that 1.0, the correlation coefficient of 1.0, what that actually means is if you were to sketch the scatter plot, you'd get a straight line. Okay? That's what the correlation coefficient of 1.0 means, right? That the relationship is exactly affine or exactly linear, right? There's a deterministic relationship, okay? And similarly, all of these, so this, for example, case also corresponds to the correlation coefficient of 1.0, correlation coefficient of 1.0. This is also 1.0. And the important point here is that all of these, for all of these 4 cases, the correlation coefficient stays equal to 1.0 regardless of what the slope is. And that's a point that we discussed in the last class as well. Okay? Now, these are the cases, for example, this case here, and if there are questions, just feel free to just unmute yourself and ask or raise your hand. Okay? What about this case here? Now the correlation coefficient is not exactly 1.0, but it's smaller. Remember, the correlation coefficient is always between minus 1.0 and plus 1.0. So this is a correlation coefficient of 0.8. What does that mean? That means that there is a strong linear relationship between the 2 random variables x and y, but it's not 100% linear, right? And that's, you can exactly see from the scatter plot. There is there is sort of a linear trend in between. You could observe that as I increase x, I would expect y to increase as well, or with increasing x, I would expect y to be increasing as well, but not 100%. Sometimes it will be not reside exactly on the straight line, sometimes on the top, sometimes on the bottom, but on average on the straight line. I mean, pretty much on the straight line. Okay? And that's a strong correlation of zero point 0.8. As you keep on decreasing the correlation, so zero point 0.4 is this case here, there's still a linear trend. If you there's an increase in x, right, you would expect an increase in y, but not as much. I mean, the points would not be as close to that straight line as they were, for example, in this case here, where the correlation coefficient is zero point 0.8, right? So this correlation coefficient is sort of a quantitative measure of how closely do these points or the densities or the scatter plot reside on a straight line. Okay? And this case is zero point 0. This is a correlation coefficient of 0.0. ठीक है. First off, सबसे पहले जो है what this scatter plot once again means कि it's the coefficients are more probable to be here in the center than they are on the outside. And I think it's actually drawn from a circularly symmetric distribution. It's actually radially symmetric outwards. And the correlation coefficient is zero point 0.0 here. ठीक है. What does that mean? Mohsin, can you try to guess? क्या मतलब है इसका?
Sir, it does not closely resemble either a positive perfect linear relationship or a negative perfect linear relationship.
Yes, and I, Mohsen, it does not have to be perfect, right? Any positive linear relationship or any negative linear relation. So that's what zero point 0.0 means, right? No matter how you fit a straight line, you fit it here and with a positive slope or a negative slope. I mean, it's immaterial. That's, I mean, any straight line is a bad fit. That's one of the other ways to say it. Any straight line that you try to fit onto this distribution, that will be a bad fit on it. I mean, so each straight line is as bad as the other, right? That's another way to put it. Okay. And these are the points. So this, for example, case is there's a correlation coefficient of minus 0.4, right? What does this mean? This is analogous to this case of plus 0.4, except that there's now a negative correlation. So if you increase x, I would expect y on average to decrease. Okay? And vice versa. If I increase y, I would expect x on average to decrease. Okay? And this is a minus 0.8. So now there's a stronger linear relationship, but an inverse linear relationship. And that's inverse linear relationship is stronger with this case of minus 0.8 than it is with this case of minus 0.4. Okay? And then there's this case of minus 1.0, and minus 1.0, that means there's an exact linear relationship between the two random variables, except that there's a negative linear relationship, right? The slope is negative. Okay? And similarly, you can say similar things about all of these lines in the middle, right? And the bottom row is also important, is also interesting. For all of these cases in the bottom, the correlation coefficient turns out to be 0, right? And this actually also strengthens our result that we or reaffirms the result that we derived, or the counterexample that we gave, that we discussed in the last class, which was uncorrelated random variables, right, may be dependent, right? And majority of these cases are examples of that, right? So this distribution corresponds to two random variables which are dependent on each other. These are not independent random variables, yet their correlation coefficient turns out to be 0. And the reason why the correlation coefficient is equal to 0 is because there's no one straight line which is a better fit than another straight line, right? All straight lines are as bad of a fit as any other. Okay? For all of these cases. Okay? And I think, if I am not wrong, each one of these distributions corresponds to dependent random variables, except perhaps the last one, right? I mean, this is something I know. The last one corresponds to an independent x and y, and uncorrelated, of course, as well. Okay? Are there any questions at this point? I mean, about this figure in particular? Right? No questions about this figure? Everything is clear? Right? Mohsen, since you asked, I mean, are there confusions, some things to ponder about? Gazi, go ahead.
Can we tell the independence from just looking at these graphs? कि बस ग्राफ को देख के हमें पता चल सकता है कि इंडिपेंडेंट है डिपेंडेंट है.
Yes. So, I mean, I can tell if they are dependent, right? That's easy to show. That's easy to guess. And for example, this case here, uh, I know for sure that these are dependent random variables. Why? Because first off, this is a sort of a uniform spread. Okay? So this is X and Y are uniformly distributed, but they're not uniformly distributed on a square, but rather on a diamond, right? On a rhombus, right? And what that means is that given any X, so if X equals, for example, close to this point here, -1 here, so Y will only be distributed in a small interval. But when X is close to 0, Y is going to be distributed in a bigger interval. So that means the interval on which Y is distributed actually is a function of X. And that means there's a dependency, right? And actually, each and every one of the cases here tell you exactly that. Okay? Except the last one. And that's involves a slight bit of more of a thinking, or rather reverse engineering, because I know कि कहाँ से आ रहा है. And for the example that I know of, which this corresponds to, I know that X and Y are independent. So that's a sort of a reverse engineering, if you will. I don't know कि exactly देखते साथ ही आप बता सकते हैं नहीं बता सकते. Dependency, independence का dependency का फिर भी बता सकते हैं. जी मोहसिन.
सर शुरू में मैं ये कहने पिक्चर किया था इस तरह के कोरिलेशन कोएफिशिएंट could be used as a measure of confidence over an approximated linear causal relationship between two random variables.
Okay.
उसको disprove करने के लिए मुझे एक fact पता चला था कि uncorrelatedness या correlation does not imply a
Yes.
causality.
Yes.
तो उससे disprove हो जाता है. लेकिन could you expand on that?
आपने जो whatever you said कि जी the correlation coefficient could be used to determine the confidence of a linear causal relationship. That's what you said. That's incorrect. But if you just remove that term or the causal word out of it, okay, then that's correct. So a correlation coefficient is a measure which tells you about the confidence with which a linear relationship can be fit onto those random variables. Causal निकाल दें तो फिर that's fine. ठीक है, there's no, and I'll discuss the causality and correlation in just a bit. But before this, I think Shoaib, you had your hand raised.
Yes, sir. So I've had this query for a long time. So will this diagrams be symmetric around the origin and every time we have a correlation coefficient of 0?
Yes. There has to be a symmetry involved. So that's correct. Actually, not necessarily around the origin. Okay? Shoaib, that has to be around some center. It has to be symmetric around some center.
Okay.
ठीक है, क्योंकि correlation coefficient, remember, involves covariance from which the means have been subtracted.
Yes.
So you're exactly right. Symmetry, there's a symmetry involved, and that's why you cannot fit any straight line on it. ठीक है? अच्छा. Now coming back to, there is a correlation and causality. I mean, these are two different things, right? And you'd find many articles on it. Wikipedia पे भी शायद आप देखें, वैसे Google search करें, you'll find lots and lots of material, right? Correlation does not imply causality, right? That's pretty well established. And I can give you one small example, and I'll probably share a TED talk with you as well. And if I remember correctly, TED talk में जो example थी ना, वो ये थी कि what we observe is or some data that you observe that as so X is the number of ice creams that that people eat in a day on average, right? So let's say that's a random variable, and the number of people who die due to drowning, and that's why. And you observe, if you just look at these two data points, what you would observe is um, there's a positive correlation between number of ice creams that somebody eats or the people eat and the number of people who die because of drowning, right? Does that mean कि आइसक्रीम खाने से के बाद जो है बंदा जो है डूब जाता है, right? Is there a causal relationship? What do you think? Right? This would lead you to, it may lead you to infer that there's something in the ice creams that is causing people to drown. क्यों वसन?
तो कोई intrinsic relationship हो सकता है.
Right? So there's, I mean, it's a pretty intuitive that this is not a causal. There's something else that may actually be the culprit. And that something else may be, I mean, what do you think? Anybody else? Okay. जी मोहसिन.
Sir, obesity से relate कर सकते हैं एक third variable.
Okay, maybe the obesity से ज़्यादा एक ज़्यादा obvious है शायद एक और, and that has to do with temperatures. Okay, so what we observe is that people eat more ice cream during the summers, right? And people go out for a swim in the sea during the summers more than during the winters. Okay, and in the summertime, so that means there are people who are eating more ice cream, and in the summertime there are more people drowning because there's more swimming, right? So the intrinsic cause is something else. It's not ice cream causing the drowning itself, but there is a positive correlation between ice cream and drowning. Okay, and that's because the causality जो है वो summer की वजह से है. Okay, and there's a lot of research on this. You will be able to find how do you find causal relationships? How do you causality analysis is another dimension that we are not going to be interested in this course. Okay. Okay. Any other questions before I pull this figure down? All right. Okay, let's see. Okay, now what I want to do is I want to go back to jointly Gaussian random variables, which is actually where we ended. And I said, I'm going to come back to this, and I'm keeping to my promise. So these are jointly random variables, so pairs of random variables who X and Y, and they're said to be jointly Gaussian if they joint PDF satisfies this expression. Okay? And in this expression, there are several there's several variables. There's the variable sigma X, which is the standard deviation of X. The variable sigma Y, the standard deviation of Y. Mu X is the mean of X. Mu Y is the mean of Y. And then there's a parameter rho, which is the correlation coefficient, right? So this is just some tedious looking expression, which sort of looks like a Gaussian. If you see X minus mu X divided by sigma X whole squared, I mean, that's what we saw in a Gaussian distribution, except that this now a function of X as well as Y. So there's this extra term here that we've not seen before, right? So this governs, this is a law, if you will, a jointly Gaussian law, okay? Now it can be verified, and I'm not going to do this here, which is KG, if you marginalize over Y, the distribution on X is going to turn out to be Gaussian with a mean mu X and a variance sigma X squared. Similarly, the distribution on Y is also going to be Gaussian with mean mu Y and variance sigma Y squared. So this should be sigma Y squared. And then the conditional of X given Y also turns out to be Gaussian, right? And so that's why Gaussians are very, very special. The conditional is also Gaussian, the marginal is also Gaussian, and the joint, we say they're Gaussian as well, okay? So yeah, so these are the three conclusions that I talked about. What I want to do next is just to try to visualize, I mean, so this equation, and not just focus too much on the equation itself, but rather on, if you plot this out in 3 dimensions, what do you get, right? So that's what I'm going to do next. Yeah, here you go. All right, so this is as a demo from Wolfram, which basically plots that 2-dimensional Gaussian distribution for different means. This is the mu x bar, this is the mu y bar, this is the sigma x bar, the sigma y, and as I slide these, and things are going to change, and it's going to let you visualize how the 3-dimensional part changes. Okay, and finally this is the rho, which is the correlation coefficient. Okay, now what about these things here? So this thing here is actually the 3-dimensional plot of the surface of the corresponding to the joint probability density function, right? So you have x on this dimension and y on this dimension, and the z, which is the height, actually corresponds to the function evaluated at a particular coordinate x and y. Okay, ye kya hai? What are these? What is this? Kyun Zaifa, what do you think?
So I think we've just squished that 3D plot into like a 2D plot, and the center bright spot indicates a higher probability value of the probability density function.
Good, right? So this is sort of a contour map or a color map, if you will, right? You know, this is an easy way. Isha, is that what you were about to say?
Yes, sir.
Okay, I couldn't hear you properly. I'm assuming that's what you were about to say as well. So, so this is an easy way of visualizing a 3-dimensional plot, right? Which is, and you collapse it in 2 dimensions, where the color actually represents the height, right? The brighter the color here, the more the height, and the darker the color, the less the height, right? So this is the brightest is going to be this white thing or yellowish white thing that you see, and the blues are very, very low. So that's almost 0. Okay. So this is a nice way of visualizing what the 3-dimensional plot looks like. Okay. Now, what do the mean? And you can see this is when mu x equals 0, mu y equals 0, sigma x equals 1, sigma y equals 1, and rho equals 0. And these are the values by default. And what I see is this 3-dimensional plot is sort of it's not a very nice 3-dimensional plot, but perhaps you could guess that this is sort of a Mexican hat. I mean, that's called a Mexican hat, or a bell curve, right? But that bell shape in 3 dimensions instead of 2 dimensions, as we've seen that is this earlier, right? So this is sort of a bell shape which is symmetric around the origin, right? And that symmetry is indicated by the fact that this heat map, if you will, is looks like a circle, right? This is the highest, and this is radial here, and as it goes out, it radially decays, right? And the radial decay is symmetric in a circle. Okay. Now, what happens? What do you expect would happen if I change mu x? Let's say if I bring this up to some positive value, what do you think would happen? Zen, Ali?
सिमेट्री चेंज होती जाएगी
Symmetry कैसे change होती जाएगी? What do you mean by that?
जैसे ये 0 पे इस वक्त आप देख रहे हैं
Yeah.
ज्यादा डार्क है
हाँ, तो फिर?
ये जैसे पॉजिटिव करते रहेंगे तो ये आगे जाते रहेगा
Good.
towards
Right?
positive value.
Good. So this mu x and mu y is really corresponds to the center of this shape, right? So if I change mu x to some high value, so okay, high. Okay, so it's stopped responding. Give me a minute. So you could see the link as well. And so that will allow you to play with this on your own as well. So let me try this again, right? So if I change mu to some positive value, mu x to some positive value, what we're going to observe is this bell-shaped curve just moves, and that's all that happens in the positive x direction, where the center is now going to be at x equals 1.295 and y equals 0. But everything else stays the same. It's just a shift. Okay. Similarly, if I change y to another positive value, this thing is going to shift up, right? You see that just shifted up. Okay. So the means are really telling you where is the curve centered at, right? And that's what sort of means represents anyway, especially for a Gaussian distribution. Okay, where is the highest point, or where is the center, right? So let me just bring this down and to 0, to around 0. And we know, okay, the sigma mu x and mu y just changes the mean. So from here on, let me just assume that the means are 0 and just try to visualize how does sigma x and sigma y change things. Okay, so if I change sigma x, what do you expect would happen if I increase sigma x? So Abdullah, what do you expect to happen if I increase sigma x? Remember, that's the standard deviation of x. So I see Haji Isha.
Sir, ये जो 2-dimensional plot है, इसके अंदर we will clearly be seeing a larger radius for the contour, and generally उसका spread ज़्यादा हो जाएगा of the 3-dimensional thing.
Okay, but then when you say spread, right? So I'm increasing sigma x. So spread, what do you mean by spread in what dimension?
I basically mean that जो जैसे मैंने 2-dimensional के लिए चीज़ कही है, उसी हिसाब से in the 3-dimensional plot जो हमारे पास 3-dimensional peak आ रही है, उसकी width एक तरह की कम हो जाएगी, ज़्यादा हो जाएगी.
Okay. Mohsen, want to say something?
So spread along x उसका बढ़ना चाहिए.
Okay. Huzaifa?
So the contour plot will become more elliptical towards in the x-axis.
In the x-axis. Okay, good. Right. So everybody's right. So if I change sigma x some more than the others, so if I change sigma x and increase sigma x, that's exactly what happens. What you instead of that circle, we now have an oval shape, right, or an ellipse, in which the spread is now more in the x dimension. Okay, and you can see the brightness also reduces, right? And that's actually makes sense because you go back to a single dimensional or a single Gaussian distribution. If you increase the variance, what happens is that the height actually decreases, okay, and the spread increases. It's like you're pulling it out, right? And that's exactly what happens here, except that you're pulling out you're stretching the bell curve in the x dimension. That's what happens with changing sigma x. Similarly, if I change sigma y and bring it down to approximately the same sigma x, now you're going to get a circle again, right? Except that the circle is now more spread out, and you can see this from this 3-dimensional figure as well, right? So this is more spread out, but symmetrically around the origin, right? It's not asymmetric, right? And I can do a lot of other things. If I, for example, ये और कम कर दूं, तो sigma y में spread और कम हो जाएगा, sigma x में उतना ही रहेगा, and so on and so forth, right? So the sigma x and sigma y change how basically the spread in either the x direction or the y direction. Okay, now let me bring this back to approximately 1 for both x and y, and here's the important parameter, which is rho, right, which is a correlation coefficient, if you remember. Okay, so if I change rho to, let's say, in a positive direction, which in this case is 0.576, right, what happens? Now it's you see ellipse hai, but that ellipse has changed its axis, right? The axis is no longer the xy plane or xy axis, right? The axis is rotated. So you've actually rotated the axis, okay? So that X and Y now indeed have a linear trend, if you will. And you can clearly see that by increasing X, I would tend to expect that Y also increases. And if I keep on increasing the correlation coefficient, the linear relationship is going to become stronger and stronger, right? This is what you observe. And यहाँ पे इस तरह शायद इतनी ज़्यादा visible now. Let me take it to -1, and this is going to be decreasing trend. Okay, so this is the decreasing trend, right? And what you observe is actually is singleton, right? So one is Gaussian distributed, one of the variables is Gaussian distributed, and the other one is a very, very strong linear function of the other with very, very little randomness around that linear equation. Okay, in this PDF. Okay, and you can change. मैं sigma y को ज़्यादा कर दूँ तो sigma y में दोबारा से you see here, right? So this spread changes, right, as once again, and you can play around with a lot of other things, and I'll let you do that. Any questions here? Okay, no questions. If there are no questions, I'm going to wrap this up. This is all I wanted to say, at least with this demonstration, and I'm going to go back to my notes and start writing. No questions? G. Ghazi, go ahead.
Isn't T a function of all of the four quantities above? So how are you like changing them independently and there is no effect on P?
So rho, you're talking about rho, I think, not P. Right?
Oh, it's a P is correlation coefficient.
So rho is a correlation coefficient which is independent of sigma x and sigma y.
Okay.
Okay. Ghazi, just hold on. I mean, go ahead and unmute yourself. And you may be confused because of the fact we say that the rho correlation coefficient is the covariance divided by sigma x and sigma y.
Okay. Yes.
Okay. And then that may be a cause of confusion. KG isn't the correlation coefficient actually a function of sigma x and sigma y? It turns out that there is a degree of freedom there. I mean, given sigma x and sigma y, you can change rho by changing the covariance. So covariance is not a function of those.
But covariance is the function of the means.
तो covariance is the function of the mean, लेकिन उसके अंदर एक और inherent independence है. By fixing all of this, you can still vary the covariance. ठीक है? Or the correlation coefficient. And that is clearly visible from here as well, by the way. Can you see the screen? Yeah. So there are 4 parameters that this joint distribution is a function of. Okay? The bottom line is knowing the mean, knowing both means and knowing both variances, does this mean that you know the correlation coefficient? The answer is no. The correlation coefficient can take on a whole spectrum of values between -1 and +1, depending on what the relationship between the two is. Okay? For any fixed mean, for any fixed variances. Okay?
With those 4 quantities, can't you calculate?
No.
Correlation coefficient.
So that's what I'm saying. Okay, given those 4 quantities, you cannot completely determine rho. That's what I'm trying to say.
Okay.
Okay. So there's independent parameters. I think there was sorry, Shoaib, I'll come back to you. Mohsen, you raised your hand as well before this, right?
Right, sir. So correlation coefficient was set to 0 initially, right? So when you put it to non-zero value, you're introducing correlation between x and y.
Yes.
So you're increasing the comparative spread of the data along a major axis as opposed to the minor axis, right?
On a diagonal axis, yeah.
ठीक है sir.
ठीक है, और वो exactly diagonal की क्या slope है? That actually depends on sigma x and sigma y and rho combined together. Okay, so so that's something I'll maybe leave for you to try to think about. Okay, I mean, this is not always going to be a slope of +1 or -1. Okay, this may change. but will still be a linear relationship.
Any major and minor axis.
So major और minor axis की, I mean, let's see, ये यहाँ पे change होना चाहिए. You see, the slope changes, even though the rho stays at approximately -1. But if I change sigma y and sigma x, the axis is going to change. So the axis is actually a function of all of these things combined. Okay, and this goes back to y equals ax plus b. That's which is going to give you a lot of answers. Okay, if y equals ax plus b, if you changing a changes the covariances, sorry, actually, it changes the variances relationship, but the correlation coefficient stays the same, which is equal to +1 or -1. Ali. Ali, go ahead, please.
So these all parameters are independent with each other?
Yes, they are all independent. That's the bottom line. They're all independent.
Okay.
Okay. Acha. Any other questions? Shoaib, please go ahead.
Sir, we cannot calculate the correlation. We know the formula correlation coefficient, but we cannot tell it exactly. Is it because of noise? What is the reason behind it?
There's an inherent relationship between the random variables x and y.
Okay.
ठीक है, जो एक innate उनकी quality है, innate relationship है. That's what tells you what rho should be, or that's what tells you what the correlation coefficient should be, right? It's not like something that you would be able to compute, knowing something else. Knowing just the means or just so let me put it another way. Knowing just the means and just the just the variances of x and y, rho tells you how they are jointly dependent on each other. Okay, you need rho to be able to tell what the joint relationship between x and y is. Because otherwise, mu x, mu y, sigma x, sigma y just tell you about the marginals, right? वो सिर्फ x और y की अपनी individual distributions के बारे में आपको बता रहे हैं. They don't tell you how x and y are dependent on each other. It's just like knowing the marginal distributions, right? But not knowing the joint distribution. Okay, and this goes back to, by the way, another point. Okay, I mean, why do you need the joint distribution when you have the marginals? What does the joint probability density function tell you on top of the information that you can already extract from the marginal distributions? What do you think? Gee, please let me, I need to charge my dongle. Meanwhile, I'll wait for answers. जी शोएब, आप why don't you give it a shot?
Sir, अगर दोनों independent हैं, तो we can multiply the marginals and obtain the joint PDF. And I think यहाँ पे भी independent ही हैं marginals.
Yeah, but what if they're not independent? I mean, they're not guaranteed to be independent.
So then we cannot say, exactly.
Then we cannot say anything. Right? So that what we can, or in order for us to say something, what the dependency is or is not is, we need to know the joint density function, right?
Okay.
Just knowing the marginals tells you nothing about the joint densities, right? Because there are multiple joint densities that could yield the same marginals. Okay? For two marginals, there could be many joint distributions, joint density functions that could yield the same marginals. Isliye knowing the marginals is only partial information. In order to know that dono kis aapas mein distributed hain, you need to know the joint density functions. It's just like the number of hours and you spend per week on working on something, and the output that you get at the end of the day, anybody gets at the end of the day. Those are two different random variables, and they have their own marginals, right? Right, तो marginals सिर्फ आपको नहीं बताएंगे यार how is the relationship between the two. उसके लिए आपको एक joint density function निकालना पड़ेगा, right? And it goes back to ice cream and number of people dying as well due to drowning. So you need a joint relationship, okay? And the rho tells you what that joint relationship should be for the case of Gaussian random variables. Okay. Any other questions? And I think it's time to move forward. Okay. All right. So this is where we were. These are joint Gaussian probability density functions. Okay. One thing I want to say about this. So if I just look at this, right, is that of independence and uncorrelatedness, right? So we said something about this. What did we say? Can somebody remind me? So if two random variables are independent, what can we say about their correlation coefficient? Jimosen?
So independence implies uncorrelatedness, but it does not go the other way.
Right. So that's something we concluded in the last lecture, which was if two random variables are uncorrelated, or if two random variables are independent, they must be uncorrelated. Okay, that's what we concluded. However, if two random variables are uncorrelated, they may not necessarily be independent, and we came across a counterexample. Okay, now what I want to do here is for the case of two random variables that are jointly Gaussian, and the PDF is given by this thing that you see on your screens, of this expression that you see on your screens at the top, this expression here, right? So let's try to figure out, Keji, if when are the two random variables x and y going to be uncorrelated? What value of rho means that they are uncorrelated? Ji, Salar? Salar, can you hear me? Okay, somebody other than Mohsen. Ji, Isha, please go ahead.
So would it be 0?
Yes, right. So when the correlation coefficient, as Khalid says as well, correct? Khalid, thank you. So when the correlation coefficient is 0, that's when two random variables decide to be uncorrelated. Okay, and then for this particular joint distribution that you see here, let's try to plug in rho equals 0 and see what the joint distribution turns out to be. So can you take a guess what happens? Right. So this is going to go away when rho equals 0. That means, this is going to be 0. This is going to be 0. And this entire term is going to go as well when rho equals 0. Right? So therefore, if I when rho equals 0, the joint probability density function of two random variables that are jointly Gaussian reduces to the following form. This turns out to be equal to 1 upon 2 pi times sigma x, sigma y, and then e raised to power minus x minus mu x whole squared divided by 2 sigma x squared minus y minus mu y whole squared divided by 2 sigma y squared. Right, so this is when rho equals 0. Is there anything I can say about this joint probability density function? Right? Is there anything special about this, or any form or anything that clicks you right away? Nazish, is there something that clicks you right away?
It's the product of marginal.
It's the product of
periods.
marginals, right? So I can say this is actually equal to, yeah, this is pretty nice. So this is sigma x squared, and this is e raised to power minus x minus mu x whole squared divided by 2 sigma x squared times 1 upon root 2 pi sigma y squared e raised to power minus y minus
Sorry, man.
come on. Thank you, Isha. Okay, so divided by 2 sigma y squared, right? And what do you observe? This is just a product of the marginals, right? So this is nothing but what fx of x was, and this is nothing but what fy of y was, right? And we come up with an important conclusion that when rho equals 0, the joint density function is nothing but the product of the marginals. And from here we conclude that rho equals 0 implies independence.
Sir, I'm not sure if that's with everybody, but I
think
can't
that's with
see
everybody.
anything.
Let me try the other connection. So for this particular case, we say rho equals 0 means they are independent, right? So this is, so therefore jointly Gaussian random variables are an exception in the sense as opposed to the general case where uncorrelatedness does not necessarily imply independence. Gaussian is sort of an exception in the sense that if two jointly Gaussian random variables are uncorrelated, they are guaranteed to be independent as well, and vice versa, of course, right? So that's why we like Gaussian. Gaussian satisfy many exceptions, and this is one of those. Okay, so a conclusion. Conclusion here is jointly Gaussian random variables and the variables x and y are independent if and only if they are uncorrelated, right? So there's a two-way implication here, as opposed to the general case in which there was a one-way implication. Independence implies uncorrelated in general, but for Gaussian, it's both ways. Okay. Any questions here? Okay. All right. So with this, I'm going to move to the next chapter. Sorry, not next chapter, next section of the same chapter. And this is transformation of pairs of random variables. And there are two cases here. I'm just going to discuss one of those cases as far as this course is concerned. And I'm going to leave off case 2 as something for you to go over. It's not too hard. but that's not something we're going to do formally in the course. Okay, so case one is the following. Case one is where Z is a random variable, which is a function of two random variables now, right? So remember, in the previous chapter, we said that there's one random variable, which is input to some system or some function, and then there's one output, right? So y equals g of x. And if we knew the PDF on x, we were required to find the PDF on y, right? So what this transformation, what does this do to the statistical properties of the random variable? Now the case is slightly more involved in the sense that there are two random variables which are input to a function and the output is one, right? There's only one output. And given the joint relationship between, or statistical relationship between x and y, the joint PDF between x and y, we're required to find the PDF on z, right? That's what we're required to address. And examples, for example, could be, so say z equals, the simplest I can give you is x plus y divided by 2, right? Which could correspond to the case of, for example, you have some sensors, we're measuring the same data or same parameter. And what you do is you say, in order for me to reduce noise, what I'll do is I'll take the reading of one sensor, I'll take the reading of the second sensor as well, and I will take the average. Okay. And if I know what the relationship between x and y is, my job will be try to determine, what is the statistical property, what are the statistical properties of the output z. Okay, that's one example. There are many other examples you can think of as we're going to do in this case as well, as minimum of x and y. Right? Those sensor readings are here, you say, I'm always going to pick the one which is minimum, right? Because that may for some reason be less noisy. And you say, okay, so given given x and y have some joint relationship, what is the PDF on z? Okay. So we are not going to do this very formally in the sense that we're going to derive a formula as we did in the case of a single random variable. Rather, we're just going to go about with the same approach without really deriving the formula. For each example, we're going to do this in a couple of steps, which is, you first find the CDF, and then from the CDF, you differentiate that CDF to obtain the PDF. Okay. So in particular, the process is going to be to first of all find what the CDF of z is going to be. This is just a probability that capital Z is less than or equal to small z, which is the probability that g of x, y is less than or equal to small z. And this can be determined by integrating the joint PDF of x and y with respect to dx and dy over what region? Over the region which satisfies that g of xy is less than or equal to z, right? And then, so this is step one, and the step two is going to be what? The step two is going to be just the derivative, right? So this is just equal to d by dz. It's not of the CDF, right? So these are the two steps we're going to do in each and every one of the examples we're going to come across. Okay, and I'm going to try to explain this through examples, right? So here's the first example. And that example is z equals x plus y, or the sum of two random variables. Okay. So if z equals x plus y, I'll do this step by step. The first thing I do is I'm going to compute the CDF. In order to compute the CDF, fz of z is the probability that x plus y is less than or equal to z. What is the probability that x plus y is less than or equal to z? For this, I will have to integrate the joint PDF of x and y over the region which corresponds to the sum of x and y being less than equal to small z. Okay? All right. So I'm going to keep this as a general general relationship without really talking about what f x of x y is, right? How do I do this integration, right? In order for me to do this integration, let's try to visualize what we're trying to do. So there's an xy plane, and this is x, this is y, right? And there's a x plus y equals z line. So this is going to look like this thing here. Oops. This thing here, right? So this line is x plus y equals z. So where do I need to integrate? What region do I need to integrate the joint PDF over? For all values of x and y which correspond to the sum of x and y being less than equal to z. ठीक है, तो कहाँ पे होगा वो region? जी मोहसिन?
So below the line.
Below the line, right? So this is the region you're going to be integrating over. So this is the region you're going to be integrating over. Right? And now there are two ways you can do it. There are two ways you could integrate it. You could either do it by varying y from minus infinity to plus infinity. And so you could do it two ways, right? So let me write this here. You could either do it by minus infinity is less than y is less than infinity. So you vary y from minus infinity to plus infinity, and x should always be, for each value of y that you choose, x should always be less than or equal to z minus y. Right? X plus y is less than equal to z. That means x must be less than equal to z plus y. Either this, or you could say, okay, minus infinity is less than x is less than infinity, or y must be less than equal to क्या होगा? Z minus x. Right? Is that clear? Right? Any x that I pick. जी कौन बोला? जी ईशा?
Sir, you asked if it's clear. I just said yes.
Okay, yes. Okay, good. Right. So this is this basic calculus. Okay. So I will go for this option. I will go for this option here. Right. So I will integrate over a region in which y goes from minus infinity to plus infinity, and x goes from minus infinity to z minus y. And what do I integrate? I integrate the joint PDF. Right? And ये किसके बराबर होगा? So this is the derivative. So if I differentiate or try to differentiate this thing here with respect to z, what I'm going to get? What am I going to get? So this is d by dz, and this is minus infinity to infinity, and this is minus infinity to z minus y, fxy, xy, dx, dy. Anybody who can tell me, KR, what will this be equal to? So क्यों शैला? So you're integrating with respect to z. Z सिर्फ यहाँ पे आ रहा है, जो कि यहाँ पे जाएगा x में.
सर x की जगह जो है वो z minus y आ जाएगा, और जब हम उसको y के ऊपर इंटीग्रेट करेंगे तो ये सिर्फ f of x of z minus y हो जाएगा.
Right. So the integral is going to go away, right? So the integral actually cancels with the derivative, right? This is fxy, and instead of x, you have z minus y here. And this is, I believe, इसको क्या कहते हैं? वो Leibniz rule कहते हैं. Right? If this was y minus z, then it would have been a negative sign here as well. Okay. So, but nevertheless, this is what you get, right? Now, this is fc of 6. That means that if you're adding two random variables up, right, x and y, and you're required to find the PDF of the resultant sum, that is given by this relationship. This nice relationship. इस तरह की चीज कभी देखिए कहीं पे? Actually, sorry, there's not a double derivative. This is just with respect to this integral is over y. Right, so that's the correct result. Okay, so let me talk about a specific case. So when x and y are independent, what happens? Then fxy xy is just the product of the margin, right? And this implies, what would fz of z be? Integral from minus infinity to plus infinity. This is so this is fx z minus y times fy of y integral over dy. Does this look familiar? Kyun Khalid? Have you seen this sort of an operation before anywhere?
Convolution में देखा था.
Right, so this is convolution. Right, this is convolution indeed. So this is actually convolution. And in fact, ये जो चीज आपको नजर आ रही है, if there are systems which are not time invariant, so then their response is actually specified by two variables, और वहाँ पे इस तरह की चीज इस्तेमाल होती है in order to find out the output of a linear time variant system. Okay, but that's besides the point. But the conclusion that we have is the following, which is okay, if x and y are independent, the PDF of z equals x plus y is equal to the convolution of fx of x and fy of y. Right, and by the way, you can derive the result for discrete random variables as well. So if x was discrete and y was discrete and z was equal to x plus y, then you could actually prove that the PMF of z is equal to the convolution of the PMF of x and the PMF of y, given that they are independent. Okay, that's not too hard to prove, and try doing that. Okay. Right. Any questions here before I have some time so I can do another particular specific example? All right. So for this example, let's say X is Gaussian, 0 mean, variance sigma squared. Let's say Y is also Gaussian, 0 mean, variance sigma squared, and rho xy equals 0. In other words, rho xy equals 0 for Gaussian, jointly Gaussian random variables means what? Salar, what does that mean? Isha, please go ahead.
Independence.
They are independent, right? So the X and Y are independent. Now you actually you go back and I'm not going to prove this here, by the way. If X and Y are independent and they're Gaussian, try to find Z, the PDF of Z equals X plus Y. Okay, so this is a side note. Yeah, DIY. If Z is Gaussian with mean, X is Gaussian with mean mu X and variance sigma X squared. Y is Gaussian with mean mu Y and sigma Y squared. And they're jointly Gaussian with correlation coefficient rho xy. Show that Z equals X plus Y is also Gaussian. Right, this may be a little tedious, but it's doable, right? Which yields an important result, which is that any linear combination of Gaussian random variables actually yields another Gaussian random variable, right? So that's why Gaussians are एक और वजह है जिसकी वजह से हमें Gaussian बड़े पसंद होते हैं, right? Any linear combination, I keep on making them up, and the result would still be Gaussian. You cannot say that for sure with other random variables. Okay. Right. So a uniform random variable, two uniform random variables, add them up, the result will not be uniform, right, if they're independent. Okay. उनकी PDF कैसे दिखेगी वैसे, by the way? If X and Y are uniform random variables, uniformly distributed between 0 and 1, तो X plus Y की PDF क्या होगी? क्यों गाजी? X plus Y की क्या होगी PDF?
सिर्फ ऐड हो जाएंगे क्योंकि हम उनको मल्टीप्लाई करना है
कि कन्वोल्यूशन करेंगे, राइट? जी ईशा, okay, Isha, I cannot hear you. I'm assuming you would have said.
Sir, I was saying कि convolution होगी.
Yeah, convolution से क्या आएगा result? I mean, असल में मैं ये पूछा था.
Sir, अगर उनकी width same है तो we will probably get a trapezium, I guess.
So you get a triangle. So if उनकी width अगर same है तो you get a triangle.
Yeah, मतलब अगर width same नहीं है तो फिर.
Yeah. So that's convolution. I mean, basic convolution. Okay. So this is an example. This is the last example we're going to do today. And the function is what? Function is Z equals X squared plus Y squared. Which basically would mean what, Kitty? Let's say if there was there's a robot in which there's an X coordinate of that robot and there's a Y coordinate of that robot. And you know that the X coordinate is Gaussian distributed, 0 mean, Y coordinate is Gaussian distributed, 0 mean. and you're required to find the PDF of the squared of the distance of the robot from the origin. Okay, which is z equals x squared plus y squared, right? So if this was a square root, then you would have been finding the PDF of the distance. And because there's no square root here, this is the squared of the distance from the origin. Okay, and you're required to find the PDF of z, right? And the way I go about this is just by following exactly the same principles. I will find the CDF first. The CDF is f capital Z of z equals probability capital Z is less than equal to small z. Right? This is the probability that x squared plus y squared is less than equal to z. Okay? And this will be an integral, therefore. So x squared plus y squared is less than equal to z over what? Over the fx of x times fy of y dx dy. Okay? So what is this equal to? This is double integral x squared plus y squared is less than equal to z. Fx of x is 1 upon root 2 pi times sigma squared. Okay? Fy of y also has that root 2 pi sigma squared, and therefore this is going to become 2 pi sigma squared. What about the exponentials? Exponentials are, when they multiply, they're going to be added up in the exponentials. This is x squared plus y squared divided by 2 sigma squared dx dy. Now, how do I compute this integral? जी अली किस तरह कंप्यूट करें? So आप असल में एक इंटीग्रल किस रीजन में इंटीग्रेट कर रहे होंगे, बाय द वे? x squared plus y squared is less than equal to z.
Circle.
In a circle, right? Of radius root z. इसके अंदर कर रहे होंगे. What's the best way of integrating in a circle, especially given the integrand, which also has the same? You go into the polar coordinates, right? So I just go into the polar coordinates. So going into the polar coordinates, so this is integral 1 upon 2 pi sigma squared. This is e raised to power minus r squared by 2 sigma squared. This is r times dr times d theta. Theta goes from where to where? Theta goes from 0 to 2 pi. And r goes from where to where?
0 to 1.
0 to square root of z. राइट इसका रेडियस जो है, इस सर्कल का रेडियस जो है स्क्वायर रूट ऑफ z है, राइट? What is this integral equal to? This is quite simple. Why? Because the reason why it's so simple is because this r divided by sigma squared is actually the derivative of this thing here, of r squared by 2 sigma squared. Okay? And because of which things become quite easy for us. This is integral from 0 to 2 pi, and this is 1 upon 2 pi, and this is e raised to power minus r squared by 2 sigma squared, and this is from 0 to root z, and this is d theta. Okay, there's nothing in there which is a function of d theta, so 2 pi is going to cancel with that, and so therefore this is going to be equal to 1 come on. Okay, so this is equal to 1 minus e raised to power minus z upon 2 sigma squared, right? This is fz of z, the CDF. And there's a u of z here, by the way. And the reason is because the radius can never be negative, right? So there's an underlying constraint there. And therefore, the PDF of z is 1 upon 2 sigma squared e raised to power minus z upon 2 sigma squared u of z, which is nothing but an exponential distribution, right? So this is an important result that's used in lots and lots of applications, where if x and y are independent Gaussian random variables, which are zero mean and identically distributed, and I were to compute the PDF of x squared plus y squared, that new random variable turns out to be an exponential random variable. Okay, and we'll stop here. Any questions? Once again, a robot distributed an xy coordinate system with zero mean for the x and zero mean for the y. Uska distance from the origin squared, how will that be distributed? That will be distributed as an exponential distribution. Okay, that's an important result. Okay. No questions?